This video, we're discussing parametric curves in calculus. This is the first of two parts. The questions are generally these questions listed here. So let's say we're given a couple of parametric equations, x equals x of t and y equals y of t. And we're asked to find the derivative of the function, or asked to find the derivative of y with respect to x and the second derivative of y with respect to x. We're asked to determine the slope and concavity of the curve at a particular value of the parameter or at a particular point on the curve. And we may also be asked to find the equation of a tangent line. So let's review what we talked about in the last video. In the last video, we looked at parametric curves or plane curves. And remember what a plane curve is. A plane curve is the graph of a pair of parametric equations combined with the parametric equations themselves. So the plane curve actually consists of two things. It consists of the graph, and it consists of the equations that define the graph. So if I've got x equals x of t and y equals y of t, as t goes through a range of values, we're going to sketch a curve in the xy plane. Now t may represent time. In that case, x would be the x position as a function of time and y would be the y position as a function of time. That doesn't have to represent time. But at different values of t, we would be at different locations, maybe along this curve that looks like this. And as t increases, we're going to travel in one direction or another direction along the curve. Sometimes we even go one way and then come back the other way, something like that. And we put little arrows on the curve to indicate what's called the orientation of the curve. That's the direction that we would be traveling as t increases, if it happens that we're only traveling in one direction along the curve. So that's, again, the direction that we would travel along the curve. If this was x as a function of time and y as a function of time, the direction that we go as t increases. And even if t is not representing time, this is the direction that the curve is traced out as t increases. And a general point here on the curve is given by x equals x of t and y equals y of t. And together, these two parametric equations give us this set of points. Now notice that there's no t-axis. T is implied. As t increases, we trace out the curve, but I'm actually sketching the curve in the xy plane. There's no t-axis here. That's a very important point. Now another way that we might represent a curve is with y as a function of x. Now this one's not a function because if I draw a vertical line here, the graph fails the vertical line test. But we could represent this maybe by a relation, like a circle has an equation and it's not a function. It has an equation x squared plus y squared equals r squared. Or if it was centered somewhere other than the origin, we know that the equation of a circle is x minus h squared plus y minus k squared equals r squared. And so this might be described by some other equation involving x and y. But that equation involving x and y doesn't take into account this parameter. This parameter t gives us some new information. And we can think of that in terms of well, time, usually. We'd say at a particular time or at this location and at this location, and as time increases, we can imagine that there's movement happening here. And even if it doesn't represent time, we can say as that parameter changes, we end up at a different position in the xy plane. Okay, so let's say that this was a function. Like maybe it doesn't have this piece. Maybe I'll just cut off this part of my graph so I can write y as a function of x. Well, if y is a function of x, and if it happens to be a differentiable function of x, I can find the derivative of y with respect to x in that case. The question becomes, well, what is the derivative of y with respect to x if x depends on t and if y depends on t? Well, here is our first equation. If x prime of t and y prime of t are not simultaneously 0, then the derivative of y with respect to x, which is giving us the slope of this curve, the slope of the graph at a particular xy pair. Notice that there's no derivative here with respect to time. This is, or derivative with respect to t. This is the change in y as x changes, instantaneous change in y as x changes. If x is given by x of t and y is given by y of t, you just take the derivative of y with respect to t and you divide by the derivative of x with respect to t. Now, this is not actually what happens, but it's convenient to think about it this way. You can kind of imagine this dt canceling out and you have a dy dx left. That's not actually what happens. It's not how this is defined, so don't do that. But it's a helpful mnemonic. You're just going to take the derivative of y and divide by the derivative of x. Or if you prefer prime notation rather than Leibniz notation, you can just use y prime of t over x prime of t. And this is provided that x prime and y prime are not simultaneously 0. If x prime and y prime are both 0, our curve might have a sharp corner. So if x prime and y prime are equal to 0 at a particular t value, then the slope of the curve may not be defined there. So the graph may have a sharp corner in it. So if we have a graph that looks like that, I think we did see something like that in the last video, I'll be able to find the derivative of y with respect to x over here and over here because the graph is nice and smooth. It makes sense that the derivative of y with respect to x would be well defined there because this just represents slope. It's the slope of this curve. But right here, I've got a sharp corner. Chances are that x prime of t and y prime of t are both 0 at that point. And that point is associated with a particular t value. I don't know what it is. Now, if y prime is non-zero and x prime is 0, what you have in that case is a constant divided by 0 for what would be your slope. That means the derivative is undefined as well, but that's undefined for a different reason. If you have a constant divided by 0 for your slope, that would, in a limiting sense, approach, as the denominator gets close to 0, that ratio would approach plus or minus infinity. And what that means is if your slope is plus or minus infinity, which really doesn't make sense, we just call it undefined. But if that's what this ratio is approaching, we're going to have something like what we have right here. So you'd have a tangent line, but it might be a vertical tangent line. And the slope of a vertical line is undefined. If we use the limit definition of a derivative and we try to calculate the slope at this location, we're going to get plus or minus infinity, which is the same thing that we are approaching if the numerator is approaching a constant, a non-zero constant, and the denominator is approaching 0. So if it's 0 over 0, we might have a corner. If it's a non-zero constant over 0, we'll have a vertical tangent line. And otherwise, the slope should be well defined. We should be able to calculate the slope using this ratio. Okay, so that is how we find the derivative of y with respect to x on a curve given by parametric equations. Now this is change in y with respect to x. There's no time here. So this is slope. This is still the slope of this curve at a particular x value. But now we're going to have slope of the curve written this way. So we're going to have the change in y with respect to x, which represents slope, but it's going to be written in terms of t because we're going to have y prime of t over x prime of t. So let's use that formula to answer this question over here. I've got x equals 2t, or t plus 2, excuse me, and y equals t squared plus 5t plus 4. And we're asked to find the derivative of y with respect to x and the second derivative of y with respect to x at a particular t value, which happens to be t equals -3. And then we're asked to find the slope and concavity of the graph at t equals -3. So according to our formula, all I need to do is find y prime and x prime and divide to find dy dx. So I'll just compute my derivatives. So the derivative of x with respect to t turns out to be 1. Derivative of y with respect to t is derivative of t squared, which is 2t. Derivative of a constant times t, which is a constant. And then the derivative of this 4 here is just going to be 0. So we compute y prime and x prime. And then we divide them. This is giving me slope on the curve, but in terms of the parameter. So we'll have y prime, which is 2t plus 5, divided by x prime, which is 1. So we just get 2t plus 5. So this gives me slope of the curve for slope of the graph over here. So I've got the change in y, instantaneous change in y with respect to x, but it's in terms of the parameter t. So when I'm asked for dy dx at t equals -3, all I have to do is substitute in t equals -3 over here. I've got 2 times -3 plus 5, so it's -6 plus 5, so it's -1. So we have a slope of -1. And if you're saying to yourself, okay, what does that mean? Well, that means at that particular point on the graph, the slope is -1. We go down 1 and over 1, and that's going to be the slope of the tangent line at that point. Now, if I want to actually find the point on the curve, it might be helpful to graph the curve first, and then think about where we would be on the curve when t equals -3, and then look at the tangent line. If we do all of that, we should see that the slope is -1. So they asked us to find dy dx at t equals -3. We did. First, we use the formula. We just computed y prime, we computed x prime, and we divided. And then we evaluated it at the given value of the parameter. Okay, cool. And later they say, if possible, find the slope and concavity of the graph at t equals -3. This represents slope. Remember, the first derivative gives you slope. Or the slope when t equals -3 if t represented time is -1. Now to visualize this, I think I want to try to graph this function. So I have x equals t plus 2 and y equals t squared plus 5t plus 4. And remember how we graph these plane curves? We usually, if possible, we solve one of the equations for t and then we substitute into the other one to get the rectangular equation of the curve. So I would solve this one for t. It's very easy to get t by itself there. If we subtract 2 from both sides, we get t equals x minus 2. And then I say, okay, well, what does y equal to then? Well, y was t squared plus 5 times t plus 4. But now I'm just replacing t with x minus 2. So that goes in there and there. Okay, so this is the rectangular equation of the curve. Might be a little easier for me to graph if I write this twice in FOIL. Let's just distribute and see what happens. Distribute the 5, so we get 5x minus 10 plus 4. Keep distributing. First times first is x squared. Outer times outer is negative 2x. Inner times inner is also negative 2x. So we get negative 4x. Negative 2 times negative 2 is positive 4. Collect like terms. We get negative 4x plus 5x is x. And 4 plus 4 is 8. 8 minus 10 is negative 2. So that's our function. And let's see. I believe that factors. If you're saying to yourself, Ms. Townsend, why would you factor? I'm factoring because if I can write this in factored form, I can see when this function would be equal to 0. And because I know it's a quadratic equation, I know the graph is a parabola. If I know when it's equal to 0 and I know the graph is facing up because of symmetry, I'll be able to graph this pretty quickly. Okay, so this factors. I need 2 numbers that multiply to give me 2, negative 2 that add to 1. So 2 and 1 will work if this is positive and that's negative. So that's my function. Or this is the rectangular equation of my curve. And I look back here, notice there are no restrictions on x or y. I don't have any domain or range restrictions. There are no square roots, there are no trig functions, nothing like that. So I've got these guys right here. And if I want to graph this, I can set y equal to 0 and solve for x. That will give me the x-intercepts of my graph. So I have 0 equals x plus 2 times x minus 1. So that means that x plus 2 is 0 or x minus 1 is 0. That's the only way we're getting 0 out of that product. And then we solve each of these equations for x. So I get x equals negative 2. So when y is 0, x is negative 2, the graph is going to cross right there. And when y is 0, x may also be 1. So the graph will cross right there. And I can look at the equation. I see that when x is 0, I can solve for y. When x is 0, y is negative 2. And it's a parabola, so we know it's going to look something like this. And because of symmetry of the parabola, I know that the vertex has to be halfway in between negative 2 and 1. So it's got to be over here at x equals negative 1/2, and it'll be down here somewhere. We could substitute in negative 1/2 and find the vertex if we wanted to, but I don't think it's really that important. What I'm really interested in is the point on the graph when t equals negative 3. because my goal in graphing this was to show you what the curve looked like, but also to show you that the slope of the graph at t equals -3 is equal to -1. So let's find out what our location is when t equals -3. Let's substitute in -3 for t here and -3 for t here, see what we get. So I could make a little chart of t values and the corresponding xy pairs. When t is -3, I get -3 plus 2 here. So my x value is -1. And when t is -3, let's see what y is. I get 9 minus 15 plus 4. So that's 13 minus 15. So it's -2. So the ordered pair on the graph of our parametric equations is x equals -1, y equals -2. And actually that makes sense because of the symmetry that I was talking about. This is 1/2 of a unit from the vertex, and then this is going to be 1/2 of a unit from the vertex. So the graph looks like this, roughly. Because it's so close to the vertex, I think it would make sense to find the vertex. So let's see where we would be when x equals -1/2. And let's substitute into this, well, actually, let's substitute into this version of the equation. When x equals -1/2, y is equal to -1/2 plus 2 times -1/2 minus 1. So I get 3/2 here and -3/2 here. So that's -9/4 or -2.25. And I'm writing it as -2.25 because it's helpful for me to think about it that way when I want to graph this function. Well, it's actually, I'm graphing a set of parametric equations, but hopefully you get the idea. Okay, so this is what our graph looks like. If you're saying to yourself, how did you know that the parabola was going to look like that? It's because that leading coefficient, the number in front of the x squared, is a 1. And if the number in front of the x squared is positive, we know the graph faces up. So when I factored it, I figured out where it would be 0. I know because of symmetry, the vertex has to be halfway in between those two zeros. And I also know because this is +1, the graph has to go up. So this is the shape. And I almost made the mistake of drawing an arrow there. Actually, I kind of did make that mistake. Now we only want to put arrows on here that indicate the orientation of the curve, if possible, if the curve is traced out in a single direction as t increases. Well, just looking at this, I can see what happens as t increases. As t increases, x increases, and as t increases, y increases. Say, ooh, but that doesn't look like y is not increasing the whole time. Yeah, I guess you're right. But I know that as t increases, x increases, so we're going to see something that looks like this. Now this location, that's x of -3, y of -3, which happened to be -1, -2. Like that's a point on our graph. And earlier, when we calculated the slope and we evaluated it, or we calculated dy dx and we evaluated it at t equals -3, we got -1. What does that mean? That means when I come over here to my graph, and I'm finding the slope of the curve right here, well, at that point, the slope is -1. So I go right here, and I'm going to go down 1 and over 1, and that's my tangent line. So it looks like that. Okay. So we answered the first two questions that they had for us, or maybe not in that order. We found this dy dx at t equals -3, and we used that to infer the slope of the graph at this point. So we said, when t equals -3, the slope of the graph is -1. Say, well, what does that mean? Well, at t equals -3, it turned out that we were at this location, x equals -1, y equals -2. As x increases by 1, y decreases by 1. The slope of the graph is -1 at that point. Okay. Now, you might also look at this curve and ask yourself, we're about to look at the second derivative. Might ask yourself, is the second derivative supposed to be positive or negative at that point, just from looking at it? If you're not sure, remember what the second derivative tells us. The second derivative tells us concavity of the curve. So the question is, at that point, is the graph concave upward or is it concave downward? I hope you said it was concave upward, because that's what concave upward looks like. So the graph is concave upward. I'd expect the second derivative to be positive there. Okay. So now let's work with the same functions and find the second derivative at t equals -3. And if you're saying to yourself, I don't know how to do that yet, that is completely understandable. I have not yet shown you how that works. Okay. So the second derivative of y with respect to x, this is giving us concavity. This is giving us geometric information. These derivatives with respect to t, they represent rates of change in x and y as the parameter changes. But when I take their ratio, this looks at the instantaneous change in y as x changes. This has nothing to do with t. It has everything to do with the geometry of this curve. It's telling me about slope. This is the same thing. A lot of students say, oh, I'm taking the second derivative. That's like acceleration, right? No, this is not, there's no t here. This is the instantaneous change in the instantaneous change in y with respect to x. So we're saying to ourselves, how is the slope changing at a particular point? So here's our formula. This looks a little odd. In order to find the second derivative of y with respect to x, you're going to take the derivative with respect to t of the first derivative of y with respect to x. And then you're going to divide that by dx dt. Now again, this isn't how it really works, but you can sort of imagine it working this way. You can think of that like a fraction and think of that like a fraction. You can sort of imagine the dt's reducing. And so you'd have d dy, like d squared y, over dx over dx. Dx times dx would be sort of a dx quantity squared. That's not actually what's happening, but it's sort of a helpful mnemonic. What this tells us to do is it says, okay, find the instantaneous change in y, or find the derivative of y with respect to x, and take its derivative with respect to t. And then divide by the derivative of x with respect to t. And we're going to have a problem. Okay, so that's how the second derivative is defined. But I see a problem right away. X was t plus 2. So x prime is 1. Oh wait, that's actually x prime. It's x prime. X prime is down here. That's fine. For some reason I was thinking I was going to take x double prime. I don't know why I got that in my head. since I was thinking of y double prime. Okay, so there's just going to be a 1 in the denominator. It's totally fine. And dy dx from our previous step was the derivative of y with respect to x divided by the derivative of y with respect to t over the derivative of x with respect to t. Okay, so we have all that. Earlier we did this and we got 2t plus 5 over 1. And so I've got the derivative of y with respect to x as a function of the parameter. Okay, so according to this, I'm supposed to take this answer and take its derivative with respect to t, and then divide by dx dt, which is the same as x prime. So I'm computing this. So if somebody asked me to find the second derivative of y with respect to x, I'd write down my formula. And then I would take the derivative of y with respect to x, which I just found when I found the first derivative. That's right here. I know it doesn't have any x's in it, it has a t in it, that's okay. And we're supposed to take its derivative with respect to t. And then you divide by the derivative of x with respect to t, or if you prefer, you can call that x prime. Either way is fine. I know I'm using prime notation and Leibniz notation in the same problem. It's a little unusual, that's okay. So I have a 1 down here, and the derivative of the numerator is 2. So it looks like the second derivative is always 2. Well, what does that mean? When they ask me now for the second derivative, evaluated at t equals -3, I would replace t with -3, but there's no t over here. So it's just 2. So that's the answer to that question. And then they ask you about the concavity of the graph. Well, remember what the second derivative tells us. Since that's 2, that's positive. That means the graph is concave upward. At the point x of -3, y of -3. So the graph is concave upward when t equals -3, which corresponds to a particular location in the xy plane, -1, -2, which is exactly what I see here. I see a graph that is concave upward and decreasing. The slope is -1 at that point, but the graph is concave upward. And look at it, it's concave upward all the time because that derivative is 2 all the time.